Does it look good? I think it looks good. Okay, so yeah, thank you for the invitation here. And I'm going to talk a bit about interactive search and especially our new paradigm, which Alistair already teasered on interactive search. And I'm going to start with how I ended up doing this. And it started with a story. It was in 2018 when I was sitting at a bar with my friend Tim. And Tim is a politician. We were having some beers. We were talking about his local urbanization project or something. And he suddenly asked, hey, how about a singleton? And at first I thought I misunderstood, but then, well, I wanted to talk about my science for some years now. So I went with it and said, yeah, you're talking about this in simple search when there's an object singled out by its shape from other objects, for example. And of course, Tim stared at me in disbelief, and he wasn't interested in this at all, of course. But I made a deal with him and I said, okay, we're drinking one of your singletons and I'll tell you about my singletons. And he reluctantly agreed. So I started to talk about visual dimensions and how they interact with each other. And around a minute into my explanation, he went, oh, this is not how searching works in real life, man. But then again, Tim is a politician, so I don't know what he really knows about real life. Anyway, he showed me this mobile game, which he had on his phone, and said, now this is more like real life searching, like total chaos, nothing is singled out or whatever that means. And while I don't fully agree with him, I think he had a point, and I think you all agree that there is a large difference between most of the classic lab-based search that we're doing and searching in everyday life. Classic lab-based search is fast and simple, and there's an indirect interaction with the environment. While everyday search is a lot slower, most of the time at least. We're searching in complex scenes and there's direct interaction. We're using our hands to search among stuff. And this is being investigated, for example, by Charlotte Riggs and others who did this, which I found quite neat. Searching for coins experiment on kind of a grasslands. But there's still such a large gap between these, our standard simple paradigms and kind of these paradigms that I think knowledge cannot be easily transferred. So we don't really know to which extent effects from lab-based search translate to complex everyday search. And this is when I really started to look into what were their kind of bridging paradigms to bridge the gap between simple and complex search or simple and everyday search. And I didn't find any. So I thought about what constitutes a good bridge. And I think this is part of what we want to talk about in this workshop overall, is what would be a good paradigm. And I came up with 3 things that I needed, so that I found were important. So for example, we need measurable set sizes to measure search efficiency comparable to basic searches, because this is one of the prime determinants of how we measure efficiency in lab-based experiments. We need direct interaction with the search space to observe action perception interactions and action attention interactions comparable to how it's in everyday life. And we need variability in the complexity of the search space so that we can allow researching more basic connections and the complex part and interactions. So, and I'm a little bit, this is the same picture Alistair showed before. So as you can see here, this is what we ended up after some trial and error in 2018. We ended up with this kind of chaotic arrangement of Lego bricks. In this example, you see 3 search trays, and on the left, we have an easy search. In the middle, we have a medium search with a double amount of pieces. And on the right, we have what we call the hard search with quadruple amount of the pieces. So 100, 200, and 400 pieces. And the first simple thing we wanted to see is whether we can observe these simple basic set size effects that we find classically in simple conjunction searches. And this was the case. So we basically reproduced the linear relationship between set size and search efficiency or response, overall response times. And this was quite neat. And then we adapted the paradigm, made it a little bit more structured. So in our second experiment, we had 20 displays, which were arranged randomly. And we carefully constructed the targets and distractors on each of these trays. So all trays had around similar set sizes, around 50 to 60 items. So we weren't interested in manipulating set size this time. But it's obviously easily adaptable if you just pour more Lego bricks onto the tray. We had 3 target types per display, and all targets could be found 10 times per display. So it was more like a foraging search and not like one of the single target searches. We had a couple of different setups or conditions. So in panel A, you see a classic color search. So participants had to search for color objects, colored bricks. And in panel B, you see a shape search, both of which are feature searches. And in panel C, it was a shape color conjunction search. So overall, participants searched in each tray 3 times, had to find 10 targets in each. And we did this for pragmatic reasons so that we come up with a good number of repetitions. And overall, they searched for 600 targets in around 20 to 25 minutes, which I thought was pretty good and compares well to classical lab-based experiments. So this experiment was there more as a proof of concept to show that we can find clear differences between some experimental conditions. And if we believe feature integration theory applies here, we would expect that both feature searches were faster than the conjunction searches, which was not the case. So we had the color searches were fastest, but shape searches were not, but conjunction searches were slowest. So shape searches were slowest. And the reason for this, what we thought at the time, might be that if you see an example like this, it immediately jumps to mind that color is super easily to be identified in these types of conjunction searches, while shape might be not. So I think our participant had the strategy to, if they had a color shape conjunction search, they just, if you search, for example, for a 2x4 brick in this 2x4 yellow brick in this example, they would just parallelly look for all the yellow items and then select among them serially. So that means that they can reduce their search space effectively to only 1/3 of the items. So something new now. So what's important in everyday searches is visual motor interactions. And I think most of you know about how to investigate the visual component. And I wanted to present a little bit about how we investigate the haptic component. And we used our paradigm to only basically tune out the visual component. So we did some blind Lego searching. We set up a foraging type search experiment, again, that features that contrasts feature and conjunction-based searches. And for here you can see an example of the stimuli, and note that in our haptic search, the only features are basically shape and size and maybe texture, but we didn't have texture. So feature search is, for example, 2 different cones among 2 different bricks. And conjunction search is what we thought is 1 brick and a cone among different bricks and different cones. So both target types had to be found at the same time in this experiment, 10 times each, and there were 40 distractors on each tray. So this is an example of how such a tray looked like, but remember that participants were blindfolded, so the colors have no impact here. And we wanted to see whether we find differences in the response time first, and this was clear. We see easy feature searches were easier and hard conjunction searches were harder. So we were quite pleased with our setup. And apart from that, we also looked at switching. So if you, for example, find a brick first, if it's your target, and then find a cone, that would be a switch of 2 targets. And if you find a cone and then a cone, that would be a repetition, so no switching. And the prediction would be that less switches occur when the attentional load is higher, which was for conjunction searches in our case. And what we found is indeed this is the case. So participants tend to switch less in the hard conjunction search condition. So they repeatedly search for the same targets, presumably because they have to focus so much on how the target feels like as compared to the feature searches. And we basically, this was inspired by an experiment from Annie Christiansen, a common attentional constraint with the foraging. And he did this in the visual domain with iPad touch devices. So we were pretty pleased we could reproduce it in the haptic domain. And stay tuned for Ani's talk on foraging in VR later today, because he might challenge this view of the world. Overall, we have this interactive search paradigm, and I think it has some benefits. It has disadvantages, of course, but I'm going to mention the benefits, which are measurable set sizes, direct interaction with a search space, variability in complexity of the search space. It works apparently with and without vision, so we can also look at some action parts. And it's easier setup than VR because no programming is required. Thank you very much, and Legos are fun.